Hi all. In this presentation, me and my teammates are going to discuss about a frequently discussed problem, timetable generation. Timetable generation is crucial task in many institutional bodies, but it is a really tricky problem at the same time, and making an efficient timetable is a complex one. It needs mapping various factors with each other like teacher, classroom, students, time slot, etc., such that there should not be any conflict. Efficient timetable generation is an combinatorial optimization problem with huge number of possible assignments. Even for small number of input values, we get exponentially large search space. Theoretically, it is an NP-hard problem. In short, it is like a giant puzzle with thousands of pieces which should be fitted at their proper place logically, and we need to do it fast. For our problem, we have defined set of inputs. Our solution is kind of mapping between these values. We have data of enrollment of students into courses which will be many-to-many mapping between all the students and all the courses. It can create conflict if a student is assigned in two courses which runs at the same time. A class can be of type lecture, tutorial or practical. We are considering that every subject will have lectures and practical tutorials are optional. Faculty details have list of all the faculties and set of all possible subjects which can be taught by a particular faculty. Faculty can teach multiple courses, but a course will be taught by at most two faculties. A file room number will contain room number and its seating capacity. There are some constraints on time slots such as classes must be between 8 am to 6 p.m. and 1 p.m. to 2 p.m. should be lunch break for everyone, etc. A timetable obeying all these constraints without any conflict will give a satisfiable solution. For optimal solution, we have tried to reduce number of gaps between the lectures, avoid very early or very late classes, and minimize switching of classrooms for different lectures or practicals or tutorials. The scheduling algorithm is implemented with three different approaches: constraint satisfaction using Z3, heuristic approach, and meta-heuristic approach.
Now I am going to discuss how we will solve this timetable problem using CSP method. We have the global data structure students, which is a list of tuple, and each tuple consists of roll number and subjects. The data structure subjects is a dictionary which maps subject code with lecture hour, tutorial hour, practical hour, and the lab location of the practical. Faculty is a dictionary which maps employee ID with subjects, that is authorized to teach. Rooms is a list of tuples and each tuple consists room number and capacity of that room. And we have number of students is a dictionary which maps subject with number of students enrolled on that subject. After parsing all our files, we will store our data in this global data structure. We also have days, which is a list of weekdays, and the valid time slots is also a list. Now, here we are using three types of variable. First is assignment variable, which is for our lecture hours, and we have tutorial assignment variables for tutorial hours and practical assignment variables for practical hours. These all variables are stored in a dictionary type data structure where a key which consists subject, faculty, room, day and time, and it maps to its corresponding Boolean variable. Okay, now we are going to discuss our constraints we used in this CSP problem. First, we are going to discuss our hard constraint. First constraint we are using is subject lecture count constraint. It enforces that in a particular day at most one lecture is possible, and within the given slots of days, that is within the weekdays, total L lectures possible. The second constant is student conflict constant. It ensures that a student cannot have more than one class on a particular day on a particular time. So it can have at most one class on a particular day and a particular time. Third constant is faculty conflict constants. It is also similar like student conflicts constant. It enforces that a faculty cannot have more than one class to take on a particular day and on a particular time. Room conflict constant is on in a room if we, for a particular day for a particular time no more than one class is assigned in a particular room. The next constant is room capacity constant for lecture. So, while assigning a lecture to a room, we must check if the room capacity is valid to assign that course or not. And this condition is enforced by this constraint. Similarly, we are checking room capacity constant for tutorial subject also. Now, tutorial constant. What tutorial constant do that in a weekdays it assign the number of tutorials hour that is given in our data. We have practical constant. In a practical constant, we are blocking the as given hours. Like we can have 2 hours of practical slot or 3 hours of practical slot. So we will block that period of time for our practical, and it also checks that in a week we can have at exactly one practical session. Now we have no overlap constraint, which ensures that there is no overlap between practical lecture class and tutorial constant. We also have no lab lecture tutorial constant, which enforces that lecture classes and tutorial classes must not be assigned in lab rooms. We have subject faculty limit constants, which enforces that in a subject, not more than two faculty is assigned to teach. These all are our hard constant. And now we will come to our soft constant. So it is for our how good to check how good our timetable is. So soft constants are avoid early and late slots. Like in a problem statement, it is given that we will try to avoid 8 to 9 class and 17 to 18 class. So we try to minimize this, and second constraint is minimize the student gap. If there is a gap between two subjects for a student, then we will try to minimize this gap. So this minimize student gap enforces this condition. And the last sub constraint we are using is minimize room switches for consecutive lectures. If a student have consecutive lectures, then we will try that those lectures must be assigned to the same room, so that the student must not switch between the rooms. So in this constraint, we are enforcing this objective, and we try to minimize this. And in our program, we are using this timeout function, which basically gives that we are setting a time bound, and within that time bound, it will give a solution which may not be the optimal solution, but near optimal solution, which satisfies all these hard constraint. But this soft constant need not be satisfied at that time. So that's the thing. And after all of this, we are printing our output in this manner. Like we have uh, and for tutorial assignment and practical assignment, we are printing it a subject-wise manner. And after running this code, we will get the CSV file of this.
Hi, I'm going to discuss about the meta-heuristic approach for timetable generation. So in meta-heuristic approach, we have particularly used genetic algorithm for our timetable generation. In timetable generation, firstly we will initialize some n number of solutions, random solutions with some random values. Each chromosome will contain some n number of genes depending on number of subjects, lectures, tutorials, and practicals for that subject. Let's say if we have these three subjects S1, S2 and S3. S1 with 3 lectures, 2 practical, 2 tutorial and 3 practical. S2 with 3 lectures, 2 tutorial and 0 practical. S3 with 2 lectures, 0 tutorial and 2 practical. So S1 will be formed in 6 genes, 3 for lecture, 2 for tutorial and 1 for practical, as we want our practicals to finish in one go only. S2 will be represented in 5 genes, that is 3 for lectures and 2 for tutorial. Similarly, S3 will be represented by 3 genes, 2 for lecture and 1 for practical. So in total, the chromosome representing the solution for these 3 subjects will have 14 genes. Each gene will have subject code, the type, that is lecture, tutorial or practical, the faculty, authorized faculty for that subject, room number, room allotted for that subject, day, some random day, Monday to Friday, start slot. And it will give us the integer slot value for that slot, that is from 8 a.m. to 6 p.m. in between those slot. Duration, 1 for lecture and tutorial and P for practical. Then we will calculate the fitness score for each chromosome that we have randomly initialized. The penalty will be introduced if there are constraint violation or conflict. At subject level check, we will introduce penalty if for a subject there are more than one lecture per day. The penalty will be introduced if the practical block is crossing the morning boundary or afternoon boundary. Student conflict may arise if a student has taken two subjects and both of the subjects are carried out in same time slot, then student conflict will arise and it will introduce some penalty. Faculty conflict may arise if a faculty is double booked at the same time slot. Room conflict may arise if two sessions occupy the same room at same time slot. Room capacity conflict will arise if the enrolled student in the subject are more than the room capacity for which the room is allotted. Room type enforcement, if any lecture or tutorial is assigned to lab room, then penalty will be introduced. And minor penalty will be introduced for sessions at 8 hours or 17 hours, as it is asked to avoid the 8 a.m. and the 5 p.m. to 6 p.m. slot. As now selection will take place. At random, two individuals will be selected and the one with the lower penalty will be taken forward and the other one will be rejected. Then crossover will take place. So if there are 50 solutions initialized in first step, then the penalty score for 50 will be calculated, and in selection we will get, after selection step, we will get 25 chromosomes only, as out of two only one is selected. Then crossover between two chromosome will take place, and crossover will take place in such a way that the the subject belong the gene belonging to a subject will be carried out in a block in order to maintain the subject integrity. So let's say we have S1 with 3 lectures, 2 tutorial and 3 practicals, S2 with 2 lectures and 1 tutorial. So let's say parent 1 represent a chromosome and parent 2 represent a chromosome. So parent 2 contains the gene in the represented how they are represented. So S1, the genes representing S1 are these 6 genes which are selected right now, and similarly S2 genes are S2L1, S2L2, S2T1. Similarly, parent 2 will also contain these 9 genes. Now the crossover between parent 1 and parent 2 will be carried out to form offspring 1 and offspring 2. The probability that the student subject 1 genes of parent 1 will be carried forward in offspring 1 is 0.5, and will be carried forward to offspring 2 is also 0.5. A random number will be generated if that random number is greater than 0.5, then the subject 1 genes will be carried forward to offspring 1, and if that random number is less than 0.5, then parent 1 genes for subject 1 will be carried forward to offspring 2. Similarly, in next iteration, the subject 2 genes will be carried forward either from parent 1 to offspring 1 or offspring 2. So after this, we will get, after crossover between two parents, we will get two new offspring. Now mutation in the new formed offspring will be carried taken forward for each session in an individual with some small probability, which is represented by mutation rate. A random tweak in one of the attribute will take place in each of the gene. So the random tweak can be, we can change the day to random day, we can change the start slot, we can change the faculty to some another authorized faculty, we can change the room allotted for it. Similarly, we will repeat the computation of fitness score, selection, crossover and mutation till either we get the optimal solution or till the maximum number of iterations allowed will be completed. At last, we will get the solution with the best penalty score. Thank you.
Now I'll tell you about heuristic A-star approach we used. This method blends classical A-star search with custom penalty function for timetable generation. We represent the timetable problem as a set of partial assignment states. We define a cost function g of n equal to the number of sessions already placed. We define a heuristic h of n as the penalty incurred when we complete the state measuring constraint violations. Our goal is to minimize f of n equals to g of n, guiding the search toward feasible schedules. Each state is essentially a dictionary of Boolean flags, one flag per possible lecture, tutorial, or practical slot. True means we have assigned that session, false or missing means unassigned. This compact representation lets us flip bits to explore different partial timetables. Cost g of n is simply the count of assigned sessions, so deeper states have higher g of n value. Heuristic h of n is computed by temporarily filling all unassigned slots with false, no session, and summing up penalty functions for hard constraint, violations, overlaps, and capacity, and soft constraints, gaps, and room switches. Combining them balances completeness with quality. Neighbor generation. To expand a given state, we randomly sample k of the currently unassigned session keys. We generate all 2 raised to k combinations by flipping those bits. Each new combination is a neighbor state. By controlling the value of k, we monitor the exponential branching. Now the A star loop. In the A star loop, we pop the state with the smallest f of n value from a priority queue. We complete it, that is, fill missing assignments as empty and compute its penalty. We update our best so far solution if the penalty improves. We then check whether we have reached our goal, 0 or acceptable penalty, or hit the maximum number of expansions. We generate neighbors and push them onto the frontier. This repeats until the termination. The strength and weakness of this algorithm. The strengths are it provides partial solution early, flexible penalty integration, weakness is exponential branching, and scalability challenges. Now I'll explain the flow of the code. As it can be seen, main function calls four parsers to load students, subjects, faculty, and room data from CSV files. We then parse the CSV inputs and we create three sets of Boolean variables: lecture, tutorials, practicals, each initialized to false. We set initial state equals to empty dictionary, no assignments, and launch the A star loop. Within A star, we pop the state with minimum F value. We complete the state, we compute the penalty, update the best state and penalty, check if it is goal or maximum expansions have been reached. Otherwise, we call generate neighbors to sample and flip up to 5 bits, creating new states to push onto the frontier. Once the A star ends, we extract the solution, translating the Boolean model back into a human readable timetable grid, which we then print. In conclusion, if we compare the three implementations, we can say that the scalability of CSP is low, of heuristic A star it's medium, and of genetic algorithm it's high. Optimal guarantee of CSP is possible, heuristic is not possible, genetic is also not possible, but it is stochastic. Implementation complexity is very medium for CSP, it's very high for A star, and it's medium for genetic algorithm. Memory usage is high, very high, moderate. Tuning required is low, medium, high. Partial solutions are not formed in CSP. They are formed in heuristic A star and are not formed in genetic algorithm. Runtime stability is deterministic in CSP. It's very unstable in A star and it's moderate in genetic algorithm. Convergence speed is again very slow in CSP. It's very much slow in A star and very fast in genetic algorithm. So this was our presentation about automated timetable generation using AI. Thank you for listening. Thank you for your attention.